In the second part of this lecture, we're going to talk about the discretization of the waveform using the finite element method. In finite element implementation, all the terms within the integrand are represented as vectors, and their inner products are represented as vector multiplications. Therefore, we can write in a vector format or void notation the waveform in such a form. So basically, the inner product is replaced with a transpose of a vertical vector. Then this transpose would become a row vector, multiplied with a vertical vector for the stress. And similarly for the other two integrands. Now, we move on to the discretization of this waveform. By discretization, I mean that I replace the solution, which is U, our primary unknown of interest, by a discretized nodal solution. So remember that this U is defined over the entire domain, which has an infinite number of material points. In the finite element method, we partition the domain into a finite collection of elements and nodes, and now we replaced our primary unknown as a collection of nodal degree of freedoms. So we have our U by a collection of nodal degree of freedoms A multiplied with a shape function matrix N. So N here, now we can do the variation of U, and then we obtain the shape function multiplied with the variation of the nodal degree of freedom vector, delta A. With this, we can immediately plug in the right-hand side of this equation and sort out the transpose of delta A, and then we are left with the usual F external force vector. And this same procedure was applied in linear FEM to sort out the F external force vector as well. So now we've obtained the external force vector, and we need to obtain the internal force vector, and that we need to work on the left-hand side of this equation. So the objective here is to sort out the delta A transpose, so that on the left-hand side we are left with F internal. And to do this, we need to work on the variation of E, which is our Green-Lagrange tensor. And the variation of E is related to the deformation gradient. So let's first work on the deformation gradient F. F is I plus partial U over partial X. The variation of F is simply a variation of this expression. I is identity matrix, it doesn't vary. So we shift the variation over to U. Now, this is a linear function of delta U, because this operator, partial derivative operator, is a linear operator. We just write this linear relationship by curly L. Now we can then move on to our Green-Lagrange strength tensor. We calculate its variation. We plug in this expression. I doesn't vary again, so the variation applies on this term, and it breaks into two terms. So we first apply the variation on the second term, and then the variation on the first term, and sum up. We get the variation of our E. At this stage, I'm not going to give the detailed expression of E in terms of F or delta F, but I'm just going to write out their functional relationships. The delta E, you can see, is linear in terms of delta F, because when we scale delta F by a certain factor, we get the same scaling on delta E. And this linear relationship is a function of our F. So basically, we can write the relationship between delta E and delta F by a linear function, linear map, which is parametrized by our deformation gradient F. We have come to the conclusion that delta E is linear in delta F, and delta F is linear in delta U. So we can conclude that delta E is linear in terms of delta U, and this linear map is parametrized by our deformation gradient F, which means that this linear map is a function of F. Now, because our delta U can be expressed in terms of N times delta A, we can plug in here and write delta E as a linear function of N times delta A. And again, this N here we can consider as a parameter, because once we've chosen a certain element type, it doesn't vary along the analysis. So the only variable that is changing during the analysis is delta A. So we shift the N to be a parameter of our linear map. So now we've expressed delta E as a linear function of delta A, and this linear map is itself a function of f and n. And we can sort out this linear map as a matrix, and it's usually called the B matrix. In a linear FEM, the B matrix relates strain with displacement. In a nonlinear FEM, the B matrix relates the variation of strain with the variation of displacement, nodal displacement degree of freedoms. And B is a linear function of f and n. This is an abstract sketch of what B relates to. And at this stage, we are not going into the details of how to express this B. We will demonstrate with some examples later on the exact expression of B in terms of f and n. Then with this expression, we can obtain this equation as well. The partial of E with respect to A is simply B. And that is basically the same as this equation here. Now, we can then plug in our delta E equals B times delta A to the left-hand side of our waveform, and we sort out our internal force vector. And as we already know, the internal force vector is a function of A, our nodal degree of freedom. But where does A come from in this expression? So we know that B is a linear function of f and n, and f is a function of u, and u is a function of A. So this means that B itself is a function of A. We also have our S, second pure Kirchhoff stress, being a function of our Green-Lagrange strain tensor through a constitutive law, and our Green-Lagrange strain tensor is obviously a function of our deformation, which is of course a function of our nodal degree of freedom. So this means that both B and S are a function of our nodal degree of freedom. Previously in a linear FEM, only the stress is a function of nodal degree of freedom, not the strain displacement matrix. There is a small detail that I would like to highlight, which is the fact that our n, here assumed to be a function of x, may not always be found. The analytical expression of n in terms of capital X may not always be available. So in the actual FE implementation, as I already mentioned, delta E and S are vectors, N and B are matrices. But for a very complex geometry, we may have irregularly shaped elements. And for this type of elements, even in the initial coordinate system, initial configuration, we may not be able to find n in terms of capital X. What we do, and this is the same procedure as in linear FEM, is to map this to a so-called parent coordinate system or natural coordinate system in terms of psi. And this is a perfect square from -1 to 1. And now we express the shape function n in terms of psi. And then we express the capital X, our material coordinates, in terms of shape function times some nodal coordinates, and our displacement in terms of shape function times nodal degree of freedoms. Then we can find the Jacobian, which is partial of capital X over partial of psi, and we use this Jacobian to calculate any partial derivative with respect to capital X. So whenever we want to calculate the partial derivative of something with respect to capital X, we first calculate its partial derivative with respect to psi, and then multiply with basically the inverse of Jacobian, and then we obtain what we want. So this is a workaround through mapping to the natural coordinate system, and then mapping back again by the inverse of Jacobian. Alright, so this is a side note, nothing to do with the main storyline. Having obtained our internal force vector and external force vector, the next thing to do is to calculate the tangent stiffness matrix. I would like to bring you back to this plot where we talk about iterations of an increment. So here, the important elements are the residue, which is the difference between the external force vector and the internal force vector, and the tangent stiffness. Using the two, we can then calculate the estimates of our incremental solutions and the corrections to them. So for this lecture, we assume that the external force is independent of our degree of freedom A. So there is no follower load considered for simplicity. Then our tangent stiffness matrix is directly the partial of F internal with respect to partial of A. Because now, as I mentioned earlier, both B and S are functions of A, so we need to apply the partial derivative to both terms while keeping the other constant. So we have the first term, which means that we keep the S fixed and then take the partial derivative of B transpose with respect to A. The second one is we keep the B fixed and take the partial derivative of S with respect to A. The first contribution is usually called the geometric tangent stiffness, and the second one is called the material tangent stiffness. I will explain why this is the case later. So basically, at this stage, the thing to remember is that now our tangent stiffness matrix has two contributions. Let us further analyze the first one, geometric tangent stiffness matrix. We know that B is a function of n and f. Because n is our shape function matrix, it's independent of our degree of freedom. So we only have the partial derivative of B with respect to f, and then through chain rule we have partial f over partial A. Then we can plug in the expression of f, which is I plus partial u over partial x. I is identity matrix, it doesn't change with respect to A, so we remove it. And we plug in the expression of u in terms of shape function times the degree of freedom vector. Now n again is independent of A, so this expression can be simplified, and we obtain this one. Remember that B is a linear function of f and n. This B itself is a map between the variation of Green-Lagrange strain and variation of nodal degree of freedom. This map is linear in terms of f and n, so when you take the partial derivative with respect to f, then you are left with only the dependency on n. With this conclusion, I plug in for the on the right side. On the right side, I'm left with the linear function of n multiplied with partial n over partial x. So there's only a dependency on n, which means that now my partial b over partial a is only a function of n, my shape function matrix. This means that if I plug in this expression to the integrand for K geometric stiffness matrix, then I know that my geometric stiffness matrix is only a function of n and s. So n is the shape function matrix. It doesn't vary during analysis, so we can consider it as a parameter. And the only one that's changing is s, our second Euler Kirchhoff stress. So you can see that the geometric tangent stiffness matrix is only a function of stress during analysis. That is why sometimes it's called the stress stiffness matrix. Now let's look at the second term, our material tangent stiffness matrix. We express partial of S of partial of A in terms of these dependent variables. So we have partial of S over partial E first, because S is a function of E. And then we apply the chain rule. We have a partial E over partial A. We know that partial E over partial A is B, so we can then substitute. Okay, first of all, we have partial of S over partial E is our constitutive tensor, which is C. And then we substitute B. We have then partial S over partial A being C times B. We plug in this expression to here. Then we get the familiar expression of material tangent stiffness matrix being integral over omega 0 B transpose CB dV0. If you still recall the stiffness matrix in linear FEM, it is exactly the same form here. The difference is, however, that now the B matrix is a function of our degree of freedom vector A through its dependency of F. We've pretty much finished the theoretical framework of total Lagrangian geometrical nonlinear finite element method. So we stopped here last week, where we derived the weak form, and today we've performed the finite element discretization on this weak form, by substituting the u into a shape function times our nodal degree from vector. We perform the variation of E to obtain the B matrix. And B, we found that it is a linear function of our deformation gradient and shape function. And then we substitute these quantities in, and we sorted out our internal force vector and external force vector respectively. Then we performed the partial derivative of internal force vector with respect to our degree of freedom A, and obtained our tangent stiffness matrix, which has two components because both B and S are functions of A. The first component is called the geometric stiffness matrix, and the second is called the material stiffness matrix. From functional dependency analysis, we arrive at the conclusion that the geometric stiffness matrix depends only on the stress state of the structure once we've fixed our shape functions. And then the material stiffness matrix has the same expression as the stiffness matrix in linear FEM, except that now the B matrix is changing during analysis because it depends on our degree of freedom vector A.